So welcome back. So we will talk about Massive MIMO today morning. So this is the kind of a overview of my talk at the morning. So I'll start with saying some introduction, then point-to-point MIMO we saw before as well. So we will I'll spend a few minutes on that, and then multi-user MIMO that we covered yesterday a little bit, and single cell Massive MIMO, and then multiple cell Massive MIMO, power control in Massive MIMO, and energy efficiency in Massive MIMO, and then finally I'll give you some summary. Okay, so that's the plan. So there are three fundamental truths in wireless communication. Okay, so the wireless throughput demand always increase in both mobile and fixed networks. So we are keep asking more data rate and more throughput every day. So that's one of the fundamental truth in wireless communication. So the wireless throughput demand always increase in both mobile and fixed networks. There are so many data hungry applications are coming every day that lead to demand for throughput. Usual frequency spectrum will never increase. To do wireless communication, we need a spectrum, but the spectrum is never going to increase. So we are limited with the scarce resources, which is the spectrum. Okay, so usual frequency spectrum will never increase. So usual frequency spectrum means the spectrum can travel far away, and etc. So the third, the fundamental truth is the researchers will always research on discovering spectral efficient communication techniques. So we are still doing a research on 6G to get more spectral efficiency. So researchers will always research on discovering spectral efficiency communication techniques. So one of them is Massive MIMO. So that's what we are going to consider. Tomorrow morning, I'll talk about full duplex radio, which is also another spectral efficient techniques. So three basic ways to improve efficiency of the wireless network. So this I mentioned briefly. There are three basic ways to improve the efficiency of wireless network. One is called deploying access point more densely. So what does this mean? Meaning is, so if you do a cell densification, you are bringing the base station closer to the user. By doing so, your signal to interference plus noise ratio is increased, so the channel capacity will increase. So the one of the way to enhance the spectral efficiency is deploying cell densification. And using more spectrum, also we can increase the efficiency of the wireless communication, more spectrum, but as I said, spectrum is more scarce resources, so we don't have much spectrum to support high data rate anymore. Increase spectral efficiency, so that's the one we are going to talk about, how to enhance the spectral efficiency. So Massive MIMO is one of the technology enhancing the spectral efficiency. So Massive MIMO is a scalable technology, okay, where a large number of terminals simultaneously communication through the entire space. So Massive MIMO mean here we have a large number of antennas at the base station, as I said a few times already. So this is maybe M is equal to 64 antennas, so 128 antennas, and the users are K users, let's say, okay, K users here. The M is very, very large compared to K. So if it is Okay, so if it is 64 antennas, we are talking about around 30 or less than 30 users. Okay, so MIMO, massive MIMO is a scalable technology where a large number of terminals simultaneously communicate through the entire frequency spectrum. So this the base station is simultaneously communicating to all the users same time and same frequency resources. Aggressive multiplexing due to excess number of serving antenna compared with the terminal. As I said, we have a large number of M, so aggressive multiplexing gain will be achieved. So aggressive multiplexing due to excess number of serving antennas compared to terminal. Okay. Performing the multiplexing and demultiplexing based on measured propagation characteristics rather than the assumed. We estimate the channel estimation is used. Simplify type of multiplexing and demultiplexing signal processing are needed. So we do, as I said, simple pre-coding and receiving techniques. So the base station normally do MRT, pre-coding, maximum ratio transmission. For the downlink, for the uplink, so this is for downlink. For uplink, it use MRC, maximum ratio combining. Okay, so that is a very simplified signal processing techniques compared to zero forcing or MMSE, etc. So simplified type of multiplexing and demultiplexing signal processing are needed. It is permit the same quality of service with reduced radiating power. And also, it is not going to, the base station is not going to radiate very high power as well. So there is a big array gain is created by this large number of antennas. So because of the large array gain, the power dissipation also very less. Eliminate frequency-dependent fading, simplify power control. So I will tell you in detail this massive MIMO techniques. There is a concept called channel hardening. So that channel, because of the channel hardening, it will eliminate the frequency-dependent fading and also simplify power control as well. And as I mentioned, TDD operation facilitate high mobility scenarios. Yesterday we talked about this uplink and downlink. There are possibility of two duplexing mode. One is called FDD, another one is called TDD. I told you massive MIMO 5G base stations are using a TDD concept, time division duplexing. So there is TDD mean the uplink and downlink using the same frequency, but different time. Due to TDD channel reciprocity, it can lead to support high mobility scenarios. That's what it's saying. TDD operation facilitate high mobility scenarios because of the channel reciprocity between uplink and downlink. A good service to all the terminal by simple power control. So we need to still use some power control to make the system more energy efficiency. That power control is also simplified in the case of massive MIMO scenario. So all these reason massive MIMO is very popular and nowadays deployed in 5G base stations, and you are enjoying the good performance. Kalpana, can you turn on this and this? Okay. Can you turn on this? Okay, so let's talk about point-to-point MIMO system. Okay, this is fine. This is fine. Yeah. Okay, so let's talk about before going to the massive MIMO system. Let's talk about point-to-point MIMO system. So this is a MIMO system with multiple antennas here, multiple, one user actually having a multiple antennas here. So this is the MIMO system, point-to-point MIMO system, okay, point-to-point MIMO system. So I'm going to talk about point-to-point MIMO system and multi-user MIMO system and the massive MIMO system and showing the difference on each of them, okay. So this is a point-to-point MIMO system, so multiple transmit antenna and multiple receive antenna, okay? So you can think like this is like your Wi-Fi access point, have a multiple antenna, and your laptop also have a multiple antenna receiving the signal. It's like that, okay? Assuming, we assume receiver know the channel, transmitter does not know the channel, okay? Assuming receiver know the channel, not the transmitter, the link spectral efficiency for the uplink and the downlink capacity is given by this expression. So this is the uplink capacity log determinant formula that we saw previously. So this is the uplink power. There are K antennas. Here there are K antennas, and here there are M antennas. So its uplink power is divided by K here because equal power allocation is done at the uplink. And similarly, there are M antennas, so this is the downlink power, so equal power allocation done in the base station. So this is the uplink and downlink spectral efficiency. Same log determinant formula, but different dimensions are here. This is the identity matrix with the K dimension. This is the identity matrix with the M dimension. Okay. So different, if you wanted to, this base station wanted to use another MIMO system, it had to, different terminals are orthogonally multiplexed. It had to use different frequency or subcarriers for the another users. So that's what it's saying. Different terminals are orthogonally multiplexed. Capacity scale linearly with minimum of M, K. So this is the degree of freedom gain that we talked yesterday, or spatial multiplexing gain. So capacity scale linearly with minimum M, K in rich scattering environment. So we like to have the environment in between transmitter and receiver to have a rich scattering. Then only this full potential of multiplexing gain can be achieved. We need a rich scattering. Capacity degrade in line of sight environment. Okay, so if there is a line of sight environment, there's not much rich scattering, then we will get some capacity degradation. We won't get the full multiplexing gain. Okay, capacity degrade in the line of sight environment. Advanced signal processing is required to separate the data stream. We saw this one yesterday. We need a VBLAS and DBLAS architecture. So advanced signal processing required to separate the data stream. Time required for channel estimation grows with M and K. Okay, so we need resources, more resources to estimate this matrix channel. Okay, so that's what they're saying. Time required for channel estimation grows with M and K. So this is the point-to-point MIMO system, the advantages and the disadvantages. I'm just motivating now, so compared to point-to-point system, multi-user MIMO, and then talk about massive MIMO and say the massive MIMO is a true advanced technology compared to all these things. So that's the plan. So now multi-user MIMO. Okay, so this is the point-to-point system, MIMO system that you saw in the previous slide. Now I'm showing each of these antennas. Let's say each of these antennas are given to one K users. So now that is called multi-user MIMO. So each of these, antennas are given to each of the users. So there are K users now. Here is the antennas are co-located. Here is the antennas are not co-located. So each of these antennas are given to different K users. So this is the users are not co-located. So this is called multi-user MIMO. Okay, so we will get the same capacity as before, but the users are not co-located. So this is the multi-user MIMO. Okay, so uplink and downlink some spectral efficiency. So when you talk about users are of course, not co-located. So we talk about, some capacity. Each of these capacities are, user capacities are add together. We talk about some capacity. So uplink and downlink some spectral efficiency are given by this expression here. So this is the uplink capacity. So so here, users have their own power. So this is the uplink capacity here. This is the downlink capacity. Okay, so here the downlink capacity assume channel knowledge at the transmitter. So the downlink base station will do some pre-coding. Okay, so that's what this is happening here. The pre-coding power allocations are happening here. So the downlink capacity can be optimized. So that's expression here. Okay. So splitting the multi-antenna receiver into users with single antenna, that's what I said, splitting the multi-antenna receiver with K users with single antenna. So that's what I said, splitting the multi-antenna receiver into users with single antenna. So that's the case for multi-user MIMO. Multi-user sum capacity does not decrease as compared to point-to-point system. So by separating these antennas and giving to each of the users, this capacity, sum capacity is same as this capacity as well. So there's no decrease in capacity. Okay. Channel knowledge is required both end, hence not scalable with respect to M and K. So these are the points you need to considerate. What I'm saying here, the channel knowledge is required at the both end, hence not scalable with M and K. So channel knowledge is required, and if you increase large number of antennas, you will end up estimating the channel most of the coherent time period, and there's not much time to transmit data. So that's what is saying here, channel knowledge is required both end, hence not scalable with respect to M and K. Dirty paper coding is and decoding is needed. So to get the full capacity, this guy, for the downlink full capacity, this guy need to know the channel, and then this guy need to do dirty paper coding, which is similar to the MMSC SIG that we talked yesterday. MMSC SIG is we do at the receiver, and similar techniques that we need to do is called dirty paper coding. This is we need to do at the transmitter. So these both are kind of an analog to similar to MRT and MRC, MRT at transmitter, MRC at the receiver. Similarly, MMSC SIG at the receiver and dirty paper coding at the transmitter. These are the capacity achieving signal processing techniques. These both are nonlinear techniques. They both are nonlinear techniques. Okay, so that's what it's saying. Dirty paper coding and decoding is needed. Propagation environment is almost favorable. So the environment we like to see is a risk scattering environment. It's not moving, I don't know why. So now I'm going to talk about massive MIMO now. Okay, so this is the plot for, this is the figure for the multi-user MIMO. Here is a massive MIMO. So only different here compared to this and this, we have a large number of antenna. M tends to infinity, or the large number of antennas. Okay, so base stations serve all the users over the same time and frequency resources, and the massive MIMO case, the multi-user MIMO case, the M and K are kind of a same order of magnitude. But in the massive MIMO case, M is very, very large compared to K, and we are using same time frequency to serve the users. Okay. channel state information only needed at the base station. So this is another important thing. Channel state information is only needed at the base station, not the user side. Okay, I will tell you in a minute. This is because of the channel hardening effect induced in the massive MIMO scenario. Linear precoding and decoding at the base station instead of dirty paper coding. So in the massive MIMO case, the linear precoding, the simple linear precoding, MRT, MRC is good enough. We don't need this, sick receiver or the dirty paper coding precoding. Okay, so this simplified signal processing is good enough. So linear precoding and decoding at the base station instead of dirty paper coding. These features render massive MIMO is scalable with respect to number of base station antennas. So because of this is the more spectral efficiency techniques and more scalable technology and the enhanced performance due to larger array gain, etc. So there are many advantages. So this table is showing the difference between this column is for the multi-user MIMO and this column for massive MIMO. Okay, so let's see. Okay, antennas M and K, user K. So we always in the remaining the talk, M is the number of antenna at the base station. K is the users. Each user have single antenna. Okay, K users. Okay, so multi-user MIMO, M and K are kind of a same order. M had to be bigger, but very similar to K. It's like a 16 antenna, 12 users, something like that. Okay, so that's the case for multi-user MIMO. But massive MIMO, M is very large compared to K. So we normal numbers are like if it is 64 antennas, it will serve like a 30 users, something like that. Okay, it's not very close. So M is very large compared to K. Signal processing. Nonlinear is preferred. I told you nonlinear signal processing like MMSE SIG and dirty paper coding is preferred in the multi-user MIMO, but massive MIMO, linear is near optimum. Linear receiver, MRT and MRC is good enough. Okay. Duplexing mode, so multi-user MIMO, we like to have TDD or FDD mode. Okay, so until 4G, we use multi-user MIMO. Okay, until 4G. So as I said, 4G base station mainly operate in the FDD mode. Okay, so sometime it also have TDD mode, but massive MIMO only TDD mode. Okay, with the channel reciprocities exploit. Okay, instantaneous channel known at the base station and the users. And here, massive MIMO base station only need to know the channel. I will tell you about channel hardening. Because of the channel hardening, we don't need channel state information at the user. Channel quality affected by fading. In the massive MIMO case, almost invariant because the channel random channel, I will tell you in a minute, random channel become become a deterministic quantity in the massive MIMO case because of the channel hardening. So the fading is going to be disappear in the case of massive MIMO system. Variation in user load. Okay, so if you have a, let's say if you have a K, the number of user is very large, compared to M, then we need to use scheduling. Because it can only serve K is less than M. So if you have a K greater than M in this case, we need to schedule different time or different frequencies. So scheduling is needed if K is larger than M. Okay. In this case, massive MIMO case, scheduling is seldom needed because the M is very large compared to K, so scheduling is not required. Resources allocation, rapid due to fading. Because of the fading, we need a resources allocation as well rapidly. Dynamic resources allocation is needed here. Only we need a slow, slow time scale resources allocation is needed in the Massive MIMO case. Cell edge performance, only good if the base station can cooperate. So what is this saying is, if you have a user at the cell edge, there is a possibility that more than one user can serve the user. Okay, so that is called base station cooperation. So if the user is in the cell edge having a bad channel quality to particular base station, so the adjacent base station also can do coordinate and transmit. That's called coordinated multipoint transmission in 4G, and that is possible. So that's what is saying, only good if the base station cooperate. Okay. But here in the Massive MIMO case, because of the large array gain, the cell edge users also served without any base station cooperation. So improved by array gain. Because of the large antenna, we have a bigger gain. So the cell edge user can enjoy a high quality signal. Base station cooperation, highly beneficial, only long-term coordination. So because of all these benefit, Massive MIMO is one of the technology that make the 5G deployment successful. Okay, so the first 5G base station deployment happened in around 2020. I told you there are 3 services introduced in 5G. One is called Enhanced Mobile Broadband, Enhanced Mobile Broadband, and EMBB, and ultra reliable lower latency communication, and massive machine type communication. The 5G, the first deployment is only focused on this one. Okay, they say 5G, but they didn't concentrate much on ultra reliable low latency communication or massive machine type communication. They only concentrate on this and deploy all the base station, and they say 5G is deployed, but they only concentrate here. And this the technology that doing this job is the Massive MIMO. Okay, so these things are currently upgrading the base station to improve these things. Okay, so the first deployment is mainly concentrate enhanced mobile broadband. So what is the technology they used? It's Massive MIMO. Okay. Okay. Any question? Yeah. The channel hardening is coming. Next slide. Okay. Any? Hmm.
As per yesterday's discussion,
Yeah.
the gain is the minimum of NR, NT.
Okay, yeah.
Now, as a user, now I have only single antenna.
Yeah.
Then how will I experience a gain of minimum of?
Okay, so here, okay, if you consider the total gain is minimum of m comma k, but the one user gain is going to be array gain only. So it's a total cell capacity is improved, but if you consider one user is getting the m array gain only. Array gain only, yeah.
Array gain yesterday we discussed minimum of NR.
No, minimum of m comma k is the multiplexing gain, okay? So that multiplexing gain is there if you consider cell capacity, okay?
You are telling in terms of bit width, sir?
Yeah, I think I'm explaining there is a cell spectral efficiency of the cell is minimum, that's a multiplexing gain is there. But for the user, one particular user, only the array gain is there.
So this is like the strength of the SINR will increase by M. Yesterday I showed you the slide with PPT. He has the factor of M there. So strength of the SINR will increase by M. And that is the multiplexing gain and minimum of NR comma NT. So minimum NR comma NT is multiplexing gain is what? The slope of the rate versus SNR curve at high SNR.
That M is coming in a minute in the slides, okay. Okay, so channel estimation and feedback overhead, okay. So let's, again, I'm comparing all three technology here. Okay, so here is the point-to-point MIMO system, multi-user MIMO and massive MIMO. This is the FDD case, and this is a TDD case, okay. So point-to-point system, uplink, there are K users had to send pilot, so we need a K pilot here, okay. For the downlink, there are M antennas here, so M pilot is needed for the point-to-point system. For the TDD case, also K pilot and M pilot is needed. So multi-user MIMO, so again, for the uplink, if you use FDD, K pilot, and for the downlink, M pilot had to be sent to estimate the channel, and you need to also do a channel feedback as well, okay? For the TDD, it's like this, okay? For the massive MIMO case, there are FDD case K pilot, and for the downlink M pilot, and then some feedback also required. But in the TDD, we need a K pilot for the downlink, uplink. For the downlink, we don't need channel estimation because of the channel reciprocity and the channel hardening. All these are kicking off. So because of that, we don't need this one. So because of this, it's, this is very successful here, very successful technology. So this plot slide is showing why the massive MIMO is not useful in the FDD mode. So here is the channel coherent block TC, the resources for the particular duration of the coherent time. It's multiply of coherent time into coherent bandwidth. So this is the resources, coherent block resources, okay? So if you are using FDD system, this is the kind of overhead, okay? This is the overhead. So if you use FDD system, you will be, spending more time on channel estimation and feedback, etc., not much time to do communication. But if you use TDD system, the overhead is very less, and you have more time to transmit data. So that's a message is said here. Is a scalable overhead is independent of M. So TDD is the appropriate technology for the massive MIMO. I already mentioned this is a kind of one way of illustrating this. So it's the same thing as, I can skip this one, okay? So this is the kind of a important slide for the massive MIMO, okay? So let me explain, okay? So consider uplink scenario, the receive signal can be written as this, okay? So the receive signal for the uplink can be written as this equation here. Y receive signal is equal to, there are K users, so 1 to K, HK, kth user channel, kth user information plus noise, okay? Consider, so we are, K user receive signal is received, that is Y. Let's say we wanted to estimate the kth user information. So we will do a maximum ratio combining estimator at the receiver. So consider vector, so we are, the maximum ratio combining vector is, let's say, detector is V1 for user 1, then the output of the detector can be written as this one. So the receive signal is multiplied by the maximum ratio combining vector, which is actually is going to be the channel magnitude and conjugate and divided by its magnitude. So anyway, this is the detector that we denoted as a V1, which is the channel anyway. Consider a linear detector. That's the maximum ratio combining happening for user 1, and you multiply the receive signal by that V1, and you get the user 1 data here. So if you if you write that user one information and summation of the other users, these are interference. So we are only concentrating on the user one. All other users' signals are interference. So these are the interfering users plus the noise, okay, effect. So I'm going to show it to you in a minute because of channel hardening, etc. This guy is going to be 0 in Massive MIMO, and this guy also going to be 0. So the interference and the noise are going to vanish, okay? So that's the beauty of Massive MIMO. I will tell you why it's going to be vanishing, okay? If we use a maximum ratio combining, then the V1 is 1 over M into H1. Okay, so because of the channels are a large number of antennas, the channel magnitude is M. So this is M here, okay? So if you use maximum ratio combining, this V1 is going to be 1 over M H1. So we have, you see, the signal remain, okay? Because, so this is the signal part, this is the signal part. V1 into H1 is going to be 1 over M into H1 squared. So if M tends to infinity, this is going to be 1. Since relay fading channel coefficient, the variant is 1. So you will get this is equal to 1. So interferent term is going to be vanishing. Why interferent term is vanishing? So this guy, these two are uncorrelated. The channels user 1 between user 2 are uncorrelated. So this term is going to vanish. These terms are going to vanish. Interferent is vanishing. Okay, if M tends to be large, this term will vanish because they are uncorrelated. So you will get a interference-free communication. The noise is also going to be vanish, okay? So this is the noise, okay? So noise and channels are also uncorrelated, so noise is also going to vanish. So this is the kind of a beauty of Massive MIMO. Because of the large number of, when you have a large number of antenna, this term vanish and this term vanish, you will have a interference-free communication, okay? So that's what, these 3 points are very important, okay? Signal is remain, interference vanish, and the noise is vanishing. Asymptotically, noise and interference-free communication, okay? So asymptotically, the estimation, this Y guy estimation is going to be approach, the S1 data. So interference-free communication. And also, asymptotically channel hardening. So this guy, H is a random variable, okay? But when in the Massive MIMO case, the mean is become 1, the variance is going to be 1 over M, and the M tends to be larger, the variance is very, very small, the channel is become deterministic. So that is called channel hardening, because the channel is no longer random anymore, because if we have a M is become larger, the variance is 1 over M is small, the channel become deterministic. So this is called asymptotically channel hardening, okay? So asymptotic favorable propagation achieved in relay and line of sight environment, okay? So this is the very important slide for the Massive MIMO case, okay? For just normal maximum ratio combining, your interference is vanished, your noise is vanished, and asymptotically the channel become deterministic as well. Any question? Okay, so yeah, so when if you put more antennas, your estimation, you will get interference-free and noise-free estimation. So this is the beauty of Massive MIMO. You will get, interference-free and noise-free communication. And this effect is called channel hardening. Okay, any question? Yeah.
Normally, when we take it yesterday or before a day first class, we consider few problems by considering zero mean and unit variance.
Yes, for the channel. Yeah.
Here, what is the, why significantly here we are taking mean one and variance is reciprocal of it?
Yeah. So because this is the vector now. Okay. So that's why this quality is going to be variant 1 and altogether it's mean 1 and the variant 1 over n.
My question is, what is the actual meaning of the mean and variance of the channel? Means, what it is indicating? Mean or variance? What does it indicate?
Okay, the channel is random. For the relay fading channel is random. Or if you consider only one channel coefficient, it have a mean 0 and variant 1. Then the magnitude of the channel coefficient is relay fading. That's what we say relay fading. The magnitude square is exponential distribution, all these things. Now I'm showing here, this is the vector now, and this guy have a mean 1 and variant 1 over m. So m tends to be larger, that vector become a kind of a deterministic. Even though it's a random vector, m tends to be large, it's become deterministic. So this is the important slide of Massive MIMO. If you understand this, you will appreciate the Massive MIMO. So you will get interference and noise-free communication with only MRT and MRC, maximum ratio combining and maximum ratio transmission. So here, these things are the uncorrelated, etc., are shown here. So this is the plot. So here is the channel gain, asymptotic channel hardening. You can see this guy. So if we have a large number of antennas, you can see the channel become hardened and it's become run. So if we are talking about less number of antennas, the channel is not deterministic. But if you increase the antennas, the channel is become deterministic quantity. So this is called channel hardening, asymptotically channel hardening. So here is the channel gain squared, and here is the correlated two channels. You can see they are become when you become a large antenna, this become uncorrelated and become 0 here. Okay, so that's why the interference is vanishing. If you have a large antennas, this term becomes 0. This term becomes 0. So that's why this interference becomes 0 if you have a large number of antennas. Similarly, this guy also becomes 0 as well. Okay, so if you have a large number of antennas, you are in this region. If you have a small number of antennas, the interference is not vanished. It's not vanished. If you have a large number of antennas, the interference is vanishing. Orthogonality appears quickly. This is asymptotically channel hardening, being channel become a deterministic, the variant become small. Okay, so now I think that's the main story about Massive MIMO. Now I'm going to show you some spectral efficiency plot and etc. Okay, so single cell uplink spectral efficiency. So let's consider single cell. So we are going to see multi-cell as well, but I'm considering single receive signal at the base station can be written as this. We saw that detection vector Vk, so we consider kth user signal is detected, so this you multiply by the MRC vector here, and at the receiver you will get the kth user signal, and it lead to this equation here. Okay, so don't worry here. So there are one term is added here, and the same term is subtracted here. So this is the kth user signal and interference and the noise, and the capacity is given by this expression. This is the signal plus the interference. So this is the channel, the kth user capacity. Okay, the kth user capacity is given here. Okay, it's signal power and the interference plus the noise. Okay, so this is the kth user capacity. If you add all the capital K users, you will get some capacity of the uplink. And okay, so now next I'm going to talk about the channel estimation. Okay, so channel estimation, we need a pilot sequence. There are k users here. Okay, so each of the user will use a orthogonal pilot signal. So the pilot signals are orthogonal, so they will have this property. Different pilot signals are orthogonal, so it's 0, and if it is same pilot, they have some TP is the length of the pilot sequence. Okay, so during the pilot transmission, all the k user will send the receives pilot signal. All of these k user will send a pilot signal, and during the time, the receive signal at the base station is given by this expression here. Okay, this expression here, all the k user pilot signals are summed together, and the k user channel can be kth user channel can be estimated by multiplying this guy with this pilot and divide by its magnitude. You will get the channel. Okay, so this is the channel estimation. Okay, this is the channel estimation. The receive signal due to pilot multiplied by the kth user pilot, you will get the kth user channel. Okay, so you can see this is the kth user channel. This is the noise term as well. So the channel estimation is given here. This is the channel estimation here. You can see this one is okay. You can write like this. The estimation error covariant. This is the error covariant. The true channel minus estimation error covariant is given. You can derive like this. Okay. There are a lot of studies have been done on this Massive MIMO for last kind of more than 15 years. So, so the channel estimation error is this, and the channel estimation is this. And if you, increase, it's also asymptotically error-free estimation you can achieve as well if you have this term tends to infinity. Okay, so receiver structure for uplink. So there are, we saw yesterday 3 receivers. One of them is MRC. That's what I already presented in a few slides ago. MRC is, this is the receiver for MRC, maximum ratio combining. This is the receiver for zero forcing, and this is the receiver for the MMSE. Okay, so you can see this is a very simple receiver. You only use channel. And here, you need to invert this matrix. So if you are talking about Massive MIMO and all these things, these matrices have become very big to invert. So this lead to some complexities as well. These matrices are, bigger matrices to invert. So that's why, people deployed use only MRT and MRC. No need to invert these bigger matrices. So there are 3 receivers, the popular receivers, maximum ratio combining, zero forcing, and the minimum mean square error. Okay, so if you use maximum ratio combining, your capacity for the uplink maximum ratio. So each of these receiver, you can get the capacity formula, derive the capacity formula as well. So this is for the maximum ratio combining. Okay, it will lead to, this is the capacity for the kth user for the uplink maximum ratio combining. After all these results, statistical results, you can simplify the kth user rate can be reduced to this value here. So this is the array gain that we were talking about. This the M is the array gain. Okay, so this is the uplink kth user maximum ratio combining capacity. Okay, there is a channel capacity, and then each of the receiver also you can get the capacity for each of these maximum ratio combining capacity, MMSE capacity, and zero forcing capacity. So this is the capacity for the MRC for the kth user. If you use a zero forcing receiver, okay, if you use a zero forcing receiver, this is the equation after these statistical properties. You will derive this capacity here. You can see there is a gain of, gain is reduced for the MRC, zero forcing M minus K here. Remember, Here, there's a M array gain is there for the MRC, but for the zero forcing, we need to project the signal. I told you we will lose some gain, which is M minus K here because of that. But interference is reduced, but the gain also reduced as well. So this is the kind of a good slide here. The capacity of the uplink user, kth user, uplink user can be written as a nice compact formula here, okay? So the G is the array gain. G is the array gain. If you use MRC, the array gain is capital M. If you use zero forcing, array gain is M minus K. That's what I told you previously. So if you use zero forcing, the array gain become M minus K because of you are doing interference nulling. You are projecting, etc. And but if you use zero forcing, Z is the interference term. The interference is reduced for the zero forcing, but MRC, the interference is high. So there is a kind of a trade-off. Again, you won't get everything. So MRC, maximum array gain, M, but full interference is there. Full interference is there. For zero forcing, reduce array gain because the M minus K, but reduce interference as well. Okay. So yeah. So you won't get both. So this is the kind of a rate versus number of antenna plot here for 2 signal to noise ratio. One is 0 dB and one is 5 dB. For 0 dB, you can see this is the zero forcing performance. The dotted line for the red is for the zero forcing. So this is the 0 dB for zero forcing, and this is the MRC, okay? And similarly, the zero forcing for the 5 dB here and zero forcing for the MRC for the 5 dB here. So you can see, zero forcing is going to perform better. Yeah, you can see let's consider only the solid line. Consider only the solid line, which are the 5 dB SNR case. The MRC is the black curve solid line, and the red one is the zero forcing. Of course, zero forcing is giving a good performance, but with the added huge complexity. But MRC is still with the reduced complexity is reasonably giving you the capacity as well. Okay, average uplink sum spectral efficiency as a function of number of base station antenna for different receiver scheme. So this is for the 10th user in the single cell. SNR is equal to 0 dB and 5 dB. Yeah, of course, the zero fusing is still performing better, but with added complexity. Any question? So now let's talk about downlink spectral efficiency. Downlink spectral efficiency, the channel reciprocity. So channel reciprocity mean the uplink channel HK is the uplink, the downlink channel is, people, we use traditionally the uplink channel is, let's say, HK, then the downlink channel is actually HK Hermitian. Okay, so this is the channel reciprocity. So uplink channel is HK, the downlink channel is HK Hermitian, and the received signal at the kth user is, this is downlink. Kth user can be written as this form, okay? Then if you do MRT, etc., the kth user capacity can be written as this formula here. So this is the kth user receive signal power, this is the interference, and this is the noise. Again, you will get the same equation for the similar equation to downlink case, the downlink also for MRT. So we are, for the downlink, we say MRT, maximum ratio transmission, have a gain of M, and for the zero forcing precoder, if you use a zero forcing precoder, the gain is reduced to M minus K. So the MRT give you maximum array gain of M, zero forcing give you reduced array gain of M minus K, but the full interference exists in the MRT case, and the reduced interference for the zero forcing, because zero forcing will null the interference. So that is because the zero forcing is even though it's the array gain is reduced, but the interference also reduced so much. That's why we are getting a zero forcing performance better compared to maximum ratio combining in the uplink case. You will see the similar performance in the downlink case as well. Okay, any question? Sorry? Yeah. Yeah, of course, linear. It's just multiplying by channel coefficient. So these are all linear. Yeah, linear receiver. The zero forcing also linear, MMSC, they are all linear receiver. So, so next, I'm going to talk about multi-cell scenario. So, so in the case of multi-cell scenario, the situation is, you need to estimate the channel. So you need to use some pilot signal to estimate the channel in this one single cell. The pilot sequence are kind of limited, okay? The pilot sequence are limited. So if you reuse the pilot again and again in a different cell, there is a pilot contamination effect, okay, which lead to channel estimation error. So that is the one we are going to see. So pilot contamination effect, okay? When you do channel estimation, and if you use the same pilot here, then there's a pilot contamination effect will lead to channel estimation error more than more, okay? So that is the effect is called here, okay? When you estimate the channel, there will be some, also there are intercell interference as well. So there are two effects. One is channel estimation effect because of the pilot contamination. The other one is if we use a universal frequency reuse, that means all the cell is using the same frequency. There is an intercell interference as well. So these are the two things will be affecting the multi-user MIMO, multi-cell scenarios. Okay, there are two effects. The channel estimation error will be more if we use pilot very often, and also there's a intercell interference. So in the capacity formula, you will have a intra-cell interference. That is the cell interference is called intra. This is the interference inside the cell, then intercell interference. This is a interference between the cells, okay? So there's an additional term will come here in the capacity formula because of the intercell interference. And then there's a channel estimation error, as I said, pilot contamination. That will lead to some capacity degradation, okay? So let's talk about multi-cell channel estimation. Maybe we can take a break, or we can, yeah? Any question so far? We can have some discussion. Yeah, microcell is, yeah. Massive MIMO is normally used in the to cover large areas, so it's a microcells. We are talking about kilometer kind of a range. So the Massive MIMO beauty is that channel hardening, interference vanishing, noise vanishing. These are the benefit which lead to enhanced mobile broadband in 5G. Any other question? Huh? Sorry?
Because K users are having single antenna.
Yes, yes.
Each user has more than one antenna.
Yeah.
Something.
So if the user have more antennas, of course, the capacity will enhance, increase. And also, if you have more antenna, you can do a few things. So you can use interference cancellation, etc. So yeah, performance will be improved.
General in real-time scenario,
Yeah.
users are more than compared to base station.
Sorry?
Users are more than compared to base station.
No. In Massive MIMO, it's not like that. So M is very, very large compared to K. Okay. If you have, let's say, users are large, let's say if some sports event happening, a lot of users are there compared to base station, then the K user will be selected. They will be using particular subcarriers, and the other K users will be orthogonally using different subcarriers. So they will be orthogonally multiplexing. That's what they say. OFDM have a large number of subcarriers. Some of the subcarriers are allocated to K user, and the different subcarriers are allocated to other K users. So yeah, it's orthogonally multiplexed. Yeah.
Is it possible to serve M users by
Possible to?
serve M users at a time? There is a massive
Okay, Massive MIMO, if we go very, very close to M users, the theory is M is very, very large. But you can go up to, M user can go up to very close to M, but not too close. Yeah.
So receiver hardware, base station hardware will have number of RF chains. Limited by number of RF chains. It means the number of signals we can process at the base station.
Yeah.
Okay, so
But if there are M antennas, obviously MRF chains, right?
if we have MRF chain, we can serve M.
Generally,
Yeah. But in the millimeter wave case, if you have a 512 antennas, they don't have a 512 RF chain. They have a panel. They call panel. So like a let's say 512 antennas, but 32 antennas are to put as a one panel. That 32 antenna have only one RF chain. Oh, so then in that case, what you will we use a hybrid precoding, analog and digital precoding. So in that case, the interference cancellation, capabilities are reduced because the RF chain reduced. Yeah. So they call panels. Each panels have only one RF chain. Then you need to do analog precodings. Analog and digital hybrid precoding. But at the user side, we only do analog precoding. We don't do analog if we are using millimeter wave. So yeah, I think this is the beauty of the Massive MIMO. You should concentrate. The noise is vanished, the interference vanished, and you will get interference-free, noise-free communication if M tends to infinity. So maybe we can have a half an hour break. Yeah. 1 and the variant 1 over m is written here. You can see the channel coefficient is complex normal 0 mean variant 1, and this is the channel coefficient from user, kth user to m antenna, let's say. So you can get the mean 1 here, and the variant 1 over m proof is here. If you want, you can write down. Okay, so let's talk about multi-cell scenario. The multi-cell scenario, there are two issues here. One is the channel estimation. If you use the pilot again and again, you won't get accurate channel estimation. That is the reason for that is called pilot contamination effect. And then you will be also, if you use the universal frequency reuse, you will be getting the interference from other cell to from the next cell. So this is called intercell interference. So these two affect the performance of the capacity, etc. So that's what we are going to look at it today. Okay. So multi-cell channel estimation. The channel from base station J to user I in cell I is given by this notation here. So this is the base station J to user I in cell L is given by this notation. And uplink and downlink transmit powers are denoted by P and the Q. Pilot reuse factor, I will tell you what does that mean. This is 1 greater than or equal to 1, etc. So the received signal during the pilot transmission is given by this expression here. This is the training time, desired channel, and this is the interference from the pilot reuse in the adjacent cells. Okay, so here you can see here. Pilot reuse factor is 1 mean. Every cell we are using the same pilot. So this is called pilot reuse factor F is equal to 1. So in this case, channel estimation error due to pilot contamination is going to be high. Okay. Here you can see this is a pilot reuse factor 3. Mean whatever pilot we used here, we are not using in the adjacent cell, but we are using far away. So this is pilot reuse factor 3. This is pilot reuse factor 4. So we are using the pilot far away. So the pilot contamination effect will be reduced here, and it's also reduced here. It will be very high over there. So MMSC channel estimation is given by this expression here. This is the MMSC channel. This is the pilot receive signal. Why is the receive signal due to pilot transmission? And from that you will, this is the channel estimation, okay? So the error variance, etc., and depends on this gamma. The gamma is given here, etc. So I think this is, there are a lot of detail of, pilot contamination effect, channel estimation, etc. I will give you a reference at the end. That book is available free. You can download and study if you want to know all these derivations. So this is all well established by now. Yeah. So I'm going to talk about multi-cell spectral efficiency. So receive signal at the base station L can be written as here. Okay, so you can see this is the receive signal at the one of the particular base station. So you can see there are k user in the particular cell that is called intra-cell signal. Inside the cell we call intra-cell signal. The cell interference from the other cells called intercell interference, INTR. Intercell interference signal is there. We consider L cell interference here. So that's why there are two summation. Each of the cell have a k user. So this is the cell that we are interested. There are k users. So that is the summation goes from 1 to k. And there is a L cell. Each cell have a k users. That's why there are two summation here and the noise. So anyway, so the performance will be degraded because of the intra-cell interference compared to single-cell scenario. So if you use the MMSC, maximum ratio combining kind of a receiver, you will get this kind of estimation after maximum ratio combining. The received signal into maximum ratio combining is given by this expression here. You can say here, this is the term because of the intra-cell interference. That's inside the cell interference. This is the term for the intercell interference. And these two terms will come in this picture. So this is the signal to interference plus noise ratio. So in the capacity formula, we will be using signal to interference plus noise ratio. If there's no interference, we talk about SNR. But if there's interference, it is going to be signal power from the noise power plus the interference power. So it's called signal to interference plus noise ratio. So this is the kth user rate at L cell is given by, this is the signal power, and this is the interference, that interference include intra-cell interference and intercell interference altogether. So the interference will be here, this will be two terms, or one is intra and other one is inter. So this is the kind of a capacity results for the uplink case. Again, you can see, you can write down everything together here like this, nice formula here. This is, if you have a MRC receiver, this is uplink kth user at cell L. If you use maximum ratio combining, you will get M array gain here. This is the array gain G is equal to M. If you use a zero forcing, the array gain become M minus K. Okay, because you're doing some projection, and when you do projection, your receive signal, the amplitude will be reduced. That's because of that you will be getting M minus K here. And the interference term, MRC have more interference, but the zero forcing have less interference, and etc. So this is the capacity expression for uplink. And here, the capacity for the downlink case as well. This is the capacity for the downlink case. You can derive this kind of expression here. Same observation as uplink. Downlink also have array gain G for the MRT. Downlink we call MRT. Uplink we call MRC. So this is the precoding MRT gain of M. And the zero forcing case, the gain, array gain become M minus K, and MRT have a more interference, zero forcing have a less interference. There is a subtraction here. So we can also nicely derive, if the M tends to infinity, the uplink rate approach nice expression like this. This is the uplink rate, but M tends to infinity. You can derive asymptotic performance for the uplink case. Similarly, this is the downlink capacity for the kth user in the cell L, and if M tends to infinity, this approach this quality as well. So this is the asymptotic rate. Rate depends on the signal and pilot contamination, okay, etc. Okay, so in Massive MIMO, we sometimes do power control as well. So why do we need a power control in Massive MIMO? To avoid a strong interference. So if you are closer to the base station, we normally do power control. Base station like to do send you some signal saying your power is very high, please reduce it such that that's called power control. Why we need a power control? In CDMA system, power control is very, very important. But here also we use power control to reduce stronger interference, ensure all users desired level of service. If you have a strong user with a large power, this affect the other users. So to ensure that we do power control. Reduce transmit power for greater energy efficiency as well. So all these reasons, we do a power control as well. So, so this is the rate. This is the capacity plot here. These are the powers. We need to find a appropriate level of power for the K user. So the power control parameters Q1 to Qk can be obtained by solving this expression here. So what we are doing is, this is the total power. We minimize the total power subject to this constraint. This constraint is this guy. So this expression, you can take anti-log here. So it becomes 2 to the power r. Okay, and then this 1 will go other side, 2 to the power r minus 1, and this denominator will go there, and then you will get this guy. So you write this expression, only this term. So if this term is greater than this, what you are doing is you are putting a constraint on the signal to interference plus noise ratio. Okay, so you want a desired signal to interference plus noise ratio. That's what this constraint is mean, and you minimize the transmitted power. So this is the problem that need. If you solve this problem, you will get power control powers for the K users as well. Okay, so I'll repeat again. So this is the power of the K user. We wanted to allocate power such that each of the users getting a certain level of signal to interference noise ratio that is obtained from this expression. So you take a anti-log, so it's become 2 to the power r, and you take this one other side, you will get 2 to the power r minus 1, and you take the denominator other side, this is the denominator part, and you want this to be larger than this, mean you are putting a constraint on signal to interference plus noise ratio. So to make sure this signal to interference plus ratio is acceptable threshold, mean the user will get a quality of service. That is, we predefine this kind of signal to interference plus ratio is required such that we find the power. Okay, so this is the constraint optimization problem. You can solve it, and this is the way the power is allocated to each of these users. Okay, so another thing people study is called energy efficiency. Energy efficiency of the network is defined by this expression here, average sum rate divided by the power consumption. Okay, so energy efficiency also, people optimize the energy efficiency. There are many papers have been written as well. The energy efficiency definition is average sum rate divided by the power consumption. The power consumption here, the denominator term, include the transmit power and also the power consumed in the circuitry as well, circuit power. Okay, so the power consumption include transmit power and also whatever power consumed in the circuitry. Okay, so this is also we consider total power. Okay, so and the throughput, average sum power is throughput is cell density, available spectrum, and spectral efficiency. If you multiply everything there, you will get the throughput. Okay, so energy efficiency is also another parameter that we normally optimized in this cellular design. So this is the formula for energy efficiency: total sum rate divided by the power consumption. Okay, so more on multi-cell linear processing. So as I said, we use MRC and MRT. We can also use zero forcing as well. There are in the MMSE, we can do MMSE for multi-cell, MMSE for single cell. So what is the difference between these two is, in MMSE, we need to consider all the interference as well. If you consider all the multi-cell interference, this is the equation for multi-cell MMSE. If you only consider so here we are considering intra-cell interference and inter-cell interference. So that's what this is the multi-user MMSE. If it is single-cell MMSE, we are only considering intra-cell interference, inside the cell interference. Okay, so this is the kind of a regularized zero forcing, and this is a zero forcing. So these are these are all linear, receivers that we saw here. So here, the difference between multi-user MMSE and single-user MMSE, this consider both interference effect, intra-cell and inter-cell interference. This one, single-cell, only consider intra-cell, single-cell interference, and this is regularized zero forcing, and this is zero forcing. So I'm going to show you some performance. Of course, this is going to perform better because it's already include all the interference effect, so it will going to perform better. So let's see. So this is the simulation parameters that we are using in this, the results that I'm going to show you. There are number of cell is 16 cell. Cell area is 0.25 kilometers and 0.25 kilometers. This is the area of the microcell. Number of antenna per base station is M. Number of users is K. The channel gain at 1 kilometer is given by this expression. These numbers are given in the 3GPP standard documents. Okay, so this is those numbers. The path loss exponents is 3.76. You will able to get these kind of numbers from the 3GPP documents. Slow fading, standard deviation is this. Bandwidth is 20 megahertz. Receiver noise power is this. Uplink transmit power is 20 dBm. Downlink transmit power 20 dBm. The coherent block is 200. Pilot reuse factor can be 1, mean universal pilot reuse, and 4. So here we have a 1 mean we have a lot of pilot contamination effect. If it is 4, less pilot contamination effect, etc. So here you can see the results, Massive MIMO multi-cell uplink area throughput. Okay, as I said, the multi-user MMSE will, this is the average sum rate versus number of antennas here. You can see the multi-user MMSE is performing better because it takes into consideration of intra-cell and inter-cell interference, so it's performing better. The MMSE, single-cell MMSE is only considered intra-cell interference, not inter-cell interference. It is the second performance. Then the regularized zero forcing and the zero forcing and the MRC, maximum ratio combining is performance is less, but it's a less complexity as well. Okay, average uplink sum spectral efficiency function of base station antenna. This is now base station antenna. And this is the pilot reuse factor is 1. So there is a large pilot contamination effect is here. This is pilot reuse factor F is equal to 1. So I will show you the next slide, the F is equal to 2 and 3. That mean the pilot reuse factor is, pilot is not used adjacent cell, it is used in far away. Then we won't get a pilot contamination effect very severe. In that case, you will get more spectral efficiency. That's what I'm going to show you in the next slide. So here, this is the pilot reuse factor is 2, and this is a pilot reuse factor is 4. So the pilot is not used very often, very close by. So you can see the spectral efficiency is increased here. You can see here it's going up to 55 or almost 58, but compared to here, it is like a 50 here. So you can see this one is 50, almost 50, and here it is going up to 56 or 57. So because the pilot contamination effect is less here, it's also more than here, and here is the severe because the pilot reuse factor is 1 here. So everywhere we are using the same pilot for channel estimation. So it lead to a channel pilot contamination effect will lead to a channel estimation error. channel estimation error lead to less spectral efficiency. But if you use pilot reuse factor 4, the pilot contamination effect is less, you will get a larger spectral efficiency. Again, this is for the multi-user MMSE. This is the single-use MMSE. This is the regularized zero forcing and zero forcing. And this is the maximum ratio combining. So this is this whole uplink case. This is the downlink case. Again, the pilot reuse factor for 1 here. Okay, you will see the similar performance. This is a multi-user MIMO, MMSE case. This is the single-use MMSE, and this is the regularized zero forcing and zero forcing. This is the MRT, maximum ratio transmission. And here again, the same results for the pilot reuse factor 2 and the pilot reuse factor 4. And in this case, the performance is better compared to the pilot reuse factor 1. So this is the energy efficiency case, energy efficiency versus spectral efficiency. So I show you about the energy efficiency equation. So we can plot the energy efficiency versus, this is a typical results people when they study energy efficiency maximization problem, they plot this kind of results, energy efficiency versus spectral efficiency, okay? Energy efficiency versus spectral efficiency for different antennas, okay? Here M is equal to 2. This is the case for M is equal to 2, it's not massive MIMO, and M is equal to 10, M is equal to 100, M is equal to 1000. These dots are, red dots are the maximum energy efficiency, okay? The energy efficiency normally go to the peak and then reduced as well, okay? If you want a more spectral efficiency, your energy efficiency become less as well. So if you wanted to operate at the maximum energy efficiency, you need to operate at these peak points, okay? So this is the different antenna case. Energy efficiency versus spectral efficiency for different value of M. The red dot represent the point at each of the curve where energy efficiency is maximum, okay? So here we use bandwidth is 100 kilohertz, and the fixed power, the circuit power used in the circuits is 10 watts. The power, as I said, the power include both fixed power in the circuitry and the transmit power. So the fixed power is 10 watts here. I think that's all I would like to say about the Massive MIMO. There's a very nice book written by Emil Johnson, Massive MIMO network, spectral energy, and hardware efficiency. It is available online, I guess. It was available before. I don't know whether it's still available or not. So whatever results I presented, you will be able to see it in this book as well. Any question? So I think the Massive MIMO stuff is, as I said, this book is published in 7 years ago. It's a well-established theory now already. Any question? So I have the 2 more set of slides I will present maybe tomorrow. One is on full duplex radio, and other one is kind of a federated learning over Massive MIMO networks. Yeah, so maybe Navneet is going to continue some reinforcement learning. Any question?